Right, this is going to be a quick review of everything that happened in kinematics, so 1D, 2D kinematics, and some of the vocabulary and concepts that are involved. So first thing you need to know is there are scalars and vectors in physics, and that the vectors are things that include or care about direction. So things like displacement, velocity, acceleration, formulas that have those in them, like momentum, which includes velocity, or force, which includes acceleration. Those are all vectors. So it's kind of easier just to list the things that are scalars. That would be stuff like distance, speed, kinetic energy. Those are scalars because they don't care about direction. But most things in physics are vectors. And when you get vectors, you need to be able to resolve them, which means break them into components. So if you had a vector, let's say that this was 10 here, and this is a 30-degree angle, you should be able to break that into a vertical component of 5 and a horizontal component of roughly 8.66. That's called resolving. And it's important to know the vertical and horizontal components because gravity only acts in the vertical direction. It's also important because you can only add vectors if they're parallel or if they're perpendicular. So if I had a vector like that, we'll make that one 11, and that, which is 4. I can add them because they're not exactly parallel, they're anti-parallel, but you'd add them and you'd get 7, right? I can also have a vector like that and like that, and I can add them because they're perpendicular, and notice that I'm adding them head to tail, and I get the square root of 137, which I don't have memorized, but you're just using the Pythagorean theorem when they're perpendicular. So what if they're not parallel or perpendicular? Like maybe you have that vector and that vector that you want to add. Well, the easiest way to do it is to break this one into its y and its x, and then you'll have your total x and your total y, and now we're back to a perpendicular situation again. So you got to resolve vectors. You have to add them head to tail. And then there's this idea of relative velocity, which I think is probably best explained in riverboat problems. So one thing nice about riverboat problems, they're easier, in my opinion, than a projectile, because in both dimensions you have constant velocity. So let's say that you have your boat, you're trying to cross a 200-meter wide river, and the current is going 3 meters per second that way, and your boat can go 6 meters per second that way. Okay, when you cross the river, if you don't account for the current really doesn't matter in terms of how much time it takes to cross the river, because it's pushing you sideways, but it's not working against your 6, nor is it working with your 6. There is no part of this 3 that is at all in the direction of this 6. So you just take t equals d over v, a constant velocity equation, which we'll get to equations in a second here. So 200 over 6, and that's like 33.3 seconds. Meanwhile, the whole time, that whole 33.3 seconds, you're going to the right at 3. So d in the horizontal is equal to v times t. So 33.3 for 3 seconds, you're going to end up 100 meters downstream. So you went 200 meters across, 100 meters downstream. Total, you went 200 squared plus 100 squared root, really, is your travel distance. Right, now they might say, well, what's your velocity relative to the river? Or they could say relative to the shore. And kind of an important thing to remember when it comes to adding velocities is, like if I'd taken my boat and decided that I wanted to angle it upstream like that, so that I'm still going 6, if I have a component that's canceling out the current, so I must have angled it upstream at a 30-degree angle, now I have 0 velocity in the x direction. So my boat's going to end up just going straight across the river. But it's going to take me longer because I have less vertical velocity, less than 6. So it'll take longer to cross the river. As far as equations go, there are 4 uniform acceleration equations and 1 constant velocity equation. So the 1 constant velocity is just v equals d over t. The 4 acceleration ones all are missing 1 variable. So the first one is vf equals vi plus at. Notice that that doesn't mention anything about the position or the displacement. The next one that I usually think of is d equals vit plus 1/2 at squared. That one doesn't care about your final velocity. The next one doesn't mention your acceleration. You are accelerating because you have an initial final velocity that it's assumed to not be the same, and you average those and you multiply by time. Now this would only be true for uniform acceleration. If you speed up uniformly from this speed to this speed, then on average you're going the middle speed for the entire time, which gives you your displacement for the entire time. In all these equations, we're using d as displacement, which on a position time graph, if you start at the origin, your position is your displacement. And finally, v final squared equals v initial squared plus 2ad is the one without time. This is really useful for like finding your max height, because you might not know the time at which you're at your max height, but you do know you're at a final velocity of 0, at least vertically, at your max height. So this is a useful one for that. All right, for diagramming motions, we had kind of a particle model where we just said the center mass of the object could be represented by like a single dot. So if you were to look at a particle model that looked like this, you could say if all of those dots are occurring in equal time increments, that object is going at constant velocity because the dots have equal spacing, where if your dots were seeming to get further and further apart, that would be uniform acceleration. And a positive acceleration. If the dots started pretty far apart and then they were getting closer and closer and closer together, that would be deceleration, or a negative acceleration if you're going forward. Speaking of that, so we should graph these things. So there's 3 kinds of graphs we do. Position, which again is like displacement. Velocity, which is the rate of change in position. And acceleration, which is the rate of change in velocity. And these graphs are related. So if you ever have a position time graph, marker's dying here, that looks nice and constant like that, that's what we call a constant positive slope, then your velocity time graph is the rate of change in this. Well, this isn't changing at a changing rate. Position is changing at a constant rate. So we just have a constant velocity. And then the acceleration is the rate and change of this. Well, this isn't changing at all. It's staying at, let's say, 12 the whole time. So that acceleration would be just 0. Okay, but if, do a few more graphs here. We had a curve here. Now that's not a constant slope. So we're not going to have a constant velocity. We're going to have a constant acceleration. What if this was a decreasing slope? Then you would have a decreasing velocity, and you would have a negative acceleration. So these are kind of linked to each other. They kind of help us get the picture of what's happening with our motion. All right, speaking of constant velocity, so constant velocity would look like a straight line on here, a horizontal line here, and 0 on here. When we talk about constant velocity, we say that the force net is 0. If that happens for like horizontal motion. It happens when whatever's pushing or pulling is being canceled out. So it's really just the inertia of the object. So as far as units go, we typically use meters per second for constant velocity, but if you take the meters per second and you multiply by 3.6, you'll get the kilometers per hour. The reason why that trick works is there's 3,600 seconds in an hour, so you can go 3,600 times more meters in an hour, but a kilometer is 1,000 times bigger. So you can do 1,000 times less kilometers than meters. So times by 3,600 divided by 1,000, it's like timesing by 3.6. So that's a really important conversion. If you want to go the other way, you take kilometers per hour, you divide by 3.6, and you get meters per second. So the number that you're going to see of meters per second that you're going, like let's say you're going 20 meters per second, that's always a smaller number than the equivalent kilometers per hour. 72 kilometers per hour is 20 meters per second. As far as uniform acceleration goes, we use Newton's second law. So this is kind of more like inertia here. This is Newton's second law, F net equals m times a. The reason why you have a uniform acceleration is because there's a net force on you. The forces on you are not balanced. That is why you're accelerating. So this would be like if you're going down a hill, or something that's in free fall, or something that's being pushed or pulled by someone. They experience an acceleration. The vertical part of projectile motion is uniform acceleration. The horizontal is constant velocity. Free fall is probably the most common example of uniform acceleration. And then we just say A equals G, which is 9.8 or 32 in feet. There's some different units you can use for this. We usually are in meters per second squared, but I've also seen kilometers per hour per second. You have to be really careful if you use anything besides meters per second squared, because when you're putting it into an equation, like even if you put it in right here, and you have kilometers per hour per second, and then you times by seconds squared, that doesn't really cancel out to a distance. So you just have to watch your units for acceleration. I like to be meters per second squared. All right, if we do a Newton's second law problem, usually it's to find this A and then stick that in to one of these places to find some other information for kinematics. All right, the last type of acceleration I want to talk about is the centripetal acceleration, which happens when you are going in a circle at a constant speed. So when we talk about velocity going in a circle, we have linear velocity and we have angular velocity. So linear velocity is just the circumference that you do, which is 2 pi r, divided by the time for one circle, which is the period. So the further out you are, the faster you go. I'm just gonna say far out is fast. All right, angular velocity is in radians per second, which means that it's independent of the radius. Everybody goes the same radians per second, regardless of the radius. So, swing this over a little bit. It doesn't matter if you chose the inside horse or the outside horse, you're gonna make the same number of radians per second. Another unit sometimes we use is revolutions per second. Like whichever track you're listening to on a record, they're all going around the same number of times per second, so the revolutions per second are the same. When we look at the equation for centripetal acceleration, it's v squared over r, and the v that we're using